Hello, ladies and gentlemen. Today's topic of discussion is going to be resonance. Now, when you say that a compound has resonance, what it means is that the compound has more than one form. Now, we're not changing the physical arrangement, we're changing the electron arrangement. So, if something has resonance, that means that the electron setup, the where we put them, the bonds, they can be set up more than one way. There's another term that you might hear in the future, and it's called isomers. Isomers is when the same thing. The isomers is when a compound can have more than one form, but this focuses on the actual arrangement of the atoms themselves, where they're placed. Okay, so isomers focuses on the atoms themselves and where they're placed. Resonance focuses on where the electrons and bonds are drawn. Okay, so today's is for resonance. So they start off with ozone as an example, but they don't have the dots like we've been doing it in the past. So I'm actually going to do it with the dots so you can make more sense of it. So what they say here is consider the Lewis structure for ozone. You would expect the double bond to have a shorter bond length. So what they're saying is right now in ozone, the double bond is here, and you have a single bond here. So single bonds would be longer than double bonds because single bonds are weaker. We talked about that briefly. What they're saying is that when they actually study ozone, when they look at it under a microscope and they study it, both bonds are the same length. And they're saying, how is that possible if one's a single and one's a double? Well, it's one isn't just a single and the other one isn't just a double. Because of resonance, what you have is a combination of both, and I'm actually going to go through it now. Okay, so you can see they have both drawn here, but I'm going to do it manually so you can see with the dots where those structures come from. All right. So let's say we have one oxygen here. Okay, then we're going to start with the original rules, start with another oxygen here, and bond one more. We have another oxygen here. Okay. So step one, we always need to figure out how many valence electrons do we have. So we have three oxygens, right? Three oxygens. This is our centerpiece. If we have three oxygens, how many valence electrons do we have? You get 6 from each, and we have 3 of them. So that means we have 18 valence electrons. So we have 18 electrons in our bank. Okay, that is what we are working with, 18 electrons. So we drew, this is our centerpiece. We're going to call this our centerpiece. So now, first thing you do is you draw your dots on your outer ones. Okay? Draw your dots on your outer ones. Boom, boom. There you go. So how many electrons have we used up so far? Remember, each bond counts as 2. So that's 2, 4, 6, 8, 10, 12, 14, 16. We used up 16 of them. We have 2 left. So those final 2 are going to go on this one in the middle. Is everyone happy? This oxygen has its 8. This oxygen has its 8. This oxygen only has 6. 2, 4, 6. Which means in order to make this one happy, we need a double bond somewhere. Now, you can get the double bond from either the oxygen on the left or the oxygen on the right. If we get it from the oxygen on the left, these 2 electrons are going to go here. And you're going to get your double bond. Okay? So if we take those electrons and we put them there, you're going to get your double bond and you're going to end up with this. And that's what this one on the left is right here. But you can also get them from the right instead. And if you get them from the right, you end up with this, which would be the one on the right. Okay? This one right here. So you can get it from either side. And when you can do that, when you have an atom that can, or a molecule that can do that, you say that it has resonance structures. Okay? In this case, ozone, which is O3, ozone has 2 resonance structures. It's either this one with the double bond is on the right, or this one where the double bond is on the left, okay? Now, the electrons are not hopping back and forth in real life, okay? They wouldn't be hopping back and forth, a double bond here, double bond there. What happens is that you have a combination of both. So instead of one bond being longer than the other because one's a double, one's a single, what you have is a combination of both. It says the actual ozone molecule is a synthesis of these two resonance structures. So the bond length for both bonds would be somewhere between a single and a double bond, okay? So the actual molecule exists as a hybrid between the two structures, okay? But to draw them on a piece of paper, this is how we'd have to draw them. And you may actually see it drawn like this instead. So instead of them doing that, when something has a resonance form, what they sometimes do, if you study chemistry in college, you may see this. So what they'll do is they'll draw dashed lines like this. They'll draw dashed lines signifying that the double bond can be on either the one on the left or the one on the right. So you may see it drawn like that as well. Okay, so that's all resonance is. It's just when you have a compound or a molecule that can have the electrons be drawn in more than one place. In this case, we have this molecule called benzene. Benzene forms a hexagon of carbons. Okay, you get what's called a carbon ring. And if you look closely, let me zoom in a little bit. On the one to the left, you have the double bond. You have the double bonds here, here, and here. While on the right, you have the double bonds on the other spots. So you can have them on either or. We call that, again, that is resonance. Okay, that is resonance. Let me zoom out a little bit so we can read the slides. Oh, well, I wasn't expecting it to do that. So the double bonds have been relocated. Okay, benzene, this is just telling you what the origin of it is. But the point of the resonance structures, let's go back to this last little point, is the electrons are not just hopping around from place to place, and they're also not just standing still. So they're not localized. Localized meaning they stay in this one spot. It's not that they either have to pick this form or this form. They are actually delocalized. It means the electrons are free to move around the entire molecule, okay? It has a resonance structure. It can hop around from piece to piece. So you may also see it drawn like this. With the, if I do the dotted lines that I just did for the ozone, you may see something like this. So you'll just see dash lines. Again, it's pretty hard to draw with the mouse and keyboard, but you may see something like this. And instead of doing the dashes, what they do instead is they just draw a circle around the whole thing, saying that the electrons can be anywhere within the circle, which is, or anywhere within the hexagon, which is true. So that's what resonance refers to. It just means that the electron configurations or the electrons can be placed in more than one location. The worksheet focuses on resonance, so I'm actually going to just stop here. There is more about polyatomic ions, but I'll leave that for you guys to go over. Okay, so if I go to the worksheet, I'm going to do classwork number 1 with you, and I'm going to do homework number 1 with you. Ozone is actually in the slides. So if you need help with ozone, just go back to the slides, and here they go through ozone with you. Okay, they show you where the resonance structures from ozone comes from. So if you need help with ozone, look through ozone. But I'm gonna do number 1 in the classwork and number 1 in the homework with you. Okay, so I'm gonna scroll up to the top for the blank sheet. Okay, so we are doing CO3. Okay, more specifically CO3 minus 2. Okay, this is a minus 2. It's weird the way they have it written. Some of you may have gotten confused with that actually. So the minus is not like, this is not like a dash 2. It's a minus. So this is CO3. That 3 should be its subscript. -2. The -2 should be superscript, okay? Same thing here. So this is NO2. That would be -1, and that's NO3 -1. Okay, so this is CO3 -2. Okay, CO3 -2. First thing we should figure out is how many electrons are we working with? Okay, how many electrons are we working with? Carbon. How many valence electrons does carbon have? Carbon has 4. And how many of them do we have? We have 1 carbon. Oxygen gives us how many? Oxygen gives us 6. How many of those do we have? We have 3 of them. Now, the -2 tells us that we have 2 extra electrons. So then we have to add 2 more extra ones. Okay? So then you have 4 plus 18. 4 plus 18 is 22. And then 22 plus 2 gives us 24. So we have 24 electrons in our bank. That's what we're working with. Okay? Now we can start drawing the molecule. We have 2 elements. If you go back to the rules, the element that goes in the middle is the element that has the least electronegativity. Out of these 2, carbon is the least electronegative. So my carbon is going to go in the middle. Okay? And then I'm going to draw the 3 oxygens. Oxygen. Boom. And boom. Okay. The next step is to always add the dots to the outer atoms first. Okay, so let's make them happy. Okay, boom, 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 boom. Okay. How many electrons have we used up so far? So 2, 4, 6, that's 8 right here. This is another 8, so that's 16. And this is another 8, so that's 24. So we only have 24, and we've already used 24. Is everyone happy? This oxygen is happy. This oxygen is happy. This oxygen is happy. The carbon is not happy. The carbon only has 2, 4, 6. The carbon has 6 electrons, but it wants 8. This is where now we have to look for double bonds. Okay, now we have to look for where can we put double bonds. So oxygen, not oxygen, carbon, the carbon only needs 2 more electrons. So only one of these has to be a double bond. And if you look, we can get a double bond from either of them. So we can either have the double bond be here, here, or here. What does that mean? If you go back to the question, the first one asks, how many resonance structures does carbonate have? If we had 3 oxygens and we can get the double bond from either of them, that means we have, the answer to this one would be, we have 3. We have 3 resonance structures for carbonate that we can use, and I'm going to draw all of them. Okay, so we can either have this one, and remember that if you're going to do that, you have to erase the dots because they're coming from there. Okay, I'm going to speak. I wish I can copy and paste the drawings. Okay, this is version 1. Okay, that's version number 1. I'm going to draw this again just for the sake of completion. I'm going to have to redraw it 3 times. Try to speed this up a little bit. Okay, this is for just so you can see everything all at once. That's version 1. Okay, let's switch back to blue. Okay, now let's have those here. I'm going to say this is version 2. Now we're getting the dots from here. Okay, now we have the double bond from up top. And then version 3 would be where the double bond is on the right. Okay, so carbon, oxygen, oxygen, And for the sake of consistency, let me fix this one over here real quick. So notice how on this one, I took the dots from the one up top. That's actually how you want to do it, because again, you want to have the electrons as far away from each other as possible. So technically that should not be there. That should be there. And then if we do the last one, what you end up with is this. Double bond is now on the right. So these are your three resonance structures. You can get the double bond from either the one on the left, the one at the top, or the one on the right. And that's what B says. B says draw one of them. Okay, so you can pick either of those. So that's A and that's B. And then C says how do the bond lengths within the carbonate structure compare? They are the same all around, okay? They are the same all around. And if you go back to the slides, it tells you why. They are the same. So let's go back to the slides real quick. And it tells us here, the actual ozone molecule is a synthesis of these two resonance structures. It's a combination of all three of them. Okay, so with this, what it would truly look like, it's a combination of the three of these. So I guess I'll have to draw a fourth one, and I'll do the little dash lines. It would be a combination of all of them, okay? It would be a combination of all three of them. So the bond lengths would all be the same, okay? Remember I told you you may see it in this form where they draw it with dash lines, where the dash line tells you that the double bond can be in either spot, okay? It's a combination of all three. So the answer to that one is that it can be any of them. All right. They're all the same length because it can be any of them. It's a hybrid. They are not localized. So now let's do NO2. It says draw the Lewis dot structure for NO2. So let me scroll down, make sure I have some space. So we are working with, let's go back to red. NO2 minus 1. First things first, let's figure out how many electrons we're working with. Nitrogen gives us how many? Gives us 5. Okay. Oxygen gives us how many? It gives us 6. And how many of those do we have? We have 2. And then you have the minus 1, which tells us we have an extra 1. So that would be plus 1. If this was plus 1, that means we were missing an extra 1. So instead of plus 1, it would be minus. So if this was positive, that means you have to subtract electrons. If this is negative, you're adding electrons. Okay, so you may see pluses sometimes. Just know that if you see a plus, it means we lost electrons, you need to subtract. So if we add these up, this is 12. 12 plus 5 is 17. 17 plus 1 gives us, we are working with 18. Which one should go in the middle? Now when we start drawing it, remember the least electronegative one goes in the middle, and that would be, in this case, nitrogen. Okay, so we are going to draw nitrogen in the middle. One oxygen on the right, another oxygen on the left. Okay. Now let's start adding our dots to the outer ones first. 2, 4, 6, 2, 4, 6. All right, let's count out how many we've used. So we've used up 2, 4, 6, 8, 10, 12, 14. We've used up 16. And we have 18, which means we have 2 left that we can use. The nitrogen right now only has 2, 4. It needs 4 more. But I only have 2 more to work with. So now we've used up all 18. That's 8, 16, 17, 18. The oxygens are happy. They have 8. The nitrogen is not. It only has 6. 2, 4, 6. Okay? Which means, again, we need a double bond. And if you look, You can get your double bond from either the left or the right. If we do it from the right, let's do it from the right. That means those dots that were just there come here and you form a double bond. And if you count up, now we have 2, 4, this is still 8. 2, 4, 6, this is still 8. So it's 8, 8 is 16, 17, 18. So we've still only used up 18, but now everyone is happy. You can either have that or you can have it come from the left instead. Okay? So this time we don't have 3 resonance structures, we only have 2. Okay? This time we only have 2. So we can either have the one on the left or the one on the right. These are your 2 resonance structures. Okay? And that's what this, I believe number part A. How many resonance structures does nitrite have? In this case, we only have 2. And then it asks you to draw one of them. You can draw either one of the ones that you saw up there. And if it asks us the same question, how do the bond lengths compare? The bond lengths, again, would all be the same because it exists as a hybrid for all of them. And it does ask you that for number 2, okay? 2C, how do the bond lengths compare? The bond lengths would be the same amongst all of them, all right? So that's it for resonance. Hopefully you can get through without any issues. If you have any questions, again, you can always ask. Out of all the ion stuff, I would say resonance will probably make the most sense to most of you since it's just about just looking where can you get more of the electrons. But again, if you have any questions, feel free to ask. But that's it for resonance structures, and I wish you the best of luck. Take care.